Hello, and welcome back. So we're now going to look at a little bit of the sort of the geometry and the topology of the complex plane, and talk about complex valued functions a little bit. So just very basic stuff, mostly just sort of review, hopefully. All right. So geometry, we'll measure things. So we measure distance in the plane by looking at the modulus, which is really just the Euclidean distance from the origin, right? Now you can actually write this as in terms of z and z bar. You can write if you take z times z bar, you actually get the modulus squared, right? X squared plus y squared, right? And if I want to take distance between two points in C, well, I just do the same thing as I do in R or any vector space. And I just subtract the 2 points and take the modulus of that, right? That actually gives me a complete metric space. It's exactly the same metric space that we get in R2. It's a standard Euclidean metric, right? So, complete means I can take limits, Cauchy limits, Cauchy sequences, sorry, have limits, right? All right. So a little bit more geometry. So first, Cauchy-Schwarz, well, maybe not you've probably seen Cauchy-Schwarz before, but maybe not this way, right? But in the complex plane, that's what it is. The real part of z times w bar is actually the real dot product. If I think of z and w as points in R2, and so this really is the absolute value of the real dot product less than or equal to the product of the sizes of the two vectors, right? By the way, there's always somebody that says that it was the wrong name. They should be Cauchy-Schwarz Bunyakovsky, and in some sense, well, it shouldn't even be Cauchy-Schwarz. It should be just Cauchy. This is the finite dimensional version. Schwarz and Bunyakovsky did the infinite dimensional version. So, but Cauchy-Schwarz is fairly standard. So that's what we're going to call it. And using Cauchy-Schwarz, we get triangle inequality. So let's prove it. So we start with this thing, which is, it's really, this is supposed to be the positive, positive square root of x squared plus y squared. So it's, well, non-negative at least, right? So yeah, so that's the inequality. That's actually that will end up being the Cauchy-Schwarz inequality if we muck around with this thing, right? So let's see. So we expand this, and again, just like over here, right? If I take the modulus squared, I get rid of the square root, and the modulus squared of something is just that something times its conjugate, right? So that's what I'm doing here. And well, we just expand this guy, right? And now that we've expanded it, I'm gonna basically look at this guy and think of, well, what if I could write it as this kind of a square, right? Well, that's not quite right. I get get an error in there, right? But yeah, that's basically what I'm doing, right? And well, now I just write it in terms of the like this is modulus z, this is modulus w, right? And so on. And this guy over here is, something plus a bar of that something is twice the real part. So that's where I'm getting this guy, right? Well, now I'm just right? It's basically if I move this over to the other side, take the square root, get rid of the 2, I get precisely Cauchy-Schwarz. They get triangle inequality, same idea, sort of. Well, I'm going to apply Cauchy-Schwarz. So we start. Again, we do it with the squares. It's easier with the squares. So z plus w, right? Start on the left-hand side. Write it in terms of the bars. So we expand this over here, and now what we do is now this is where we're applying Cauchy-Schwarz. We look at this bit over here, and as I said, that's just like what happened from here to here, right? This is something plus the bar of that something, and that's twice the real part of that something. And so I bound it from above using Cauchy-Schwarz, right? And I leave these guys as they were. And what happens is now I can, this is just norm z, mod z squared. This is mod w squared, right? So I actually get mod z plus mod w squared, right? So I take the square root and I get the triangle inequality, right? I mean, in some sense, metric space, right? I've already said that it satisfies triangle inequality. So, but so this is the way that you would prove that it is a metric space. Let's look at the continuity of the algebraic operations, and yeah, they are continuous. I mean, if you think about it, all of these are defined as some functions of the real and imaginary parts, and those are all nice continuous functions. So you just write out what all of these are, and in terms of the real and imaginary parts, and you get immediately that they're actually that all these are continuous. Maybe the only tricky bit that you have to worry about is being able to divide here, but even that, it's basically you write out what it is and note what it means for that to be zero. All right. Now let's give some notation terminology. So we define, what do we mean by a disk? So disk of radius r centered at P or around P is it's the set of all the z in the complex plane whose distance to P is less than r, right? And we're going to write it like this: delta sub r of P. That's our notation. Now, a special disk is if P is 0 and R is 1, right? So instead of always writing this, we're just going to write it as D, this bold blackboard bold D, and we're going to call it the unit disk. All right. So that's the unit disk. There's another version. This is gonna make more sense later. Why is it a version of the unit disk? But it's called the upper half plane, and it's basically everything above the real axis, right? So it's this guy. They actually end up being essentially equivalent for all practical purposes, although they're useful for different things. So that's what we're gonna write it as H. We're gonna use D more than H, but it's also a fairly standard thing. Now, this is maybe not completely necessary, but it's standard in complex analysis. So if I have an open or open and connected set, right? So not just an open set, but a connected one, I'm going to call it a domain, right? It's maybe a little unfortunate that domain is also used for domain of a function, no matter what it is. But in some sense, that's sort of where this comes from. Like we're trying to figure out, these are sort of the natural domains of the functions that we're studying, right? So So that it's just a bit of notation, but that's what it means, right? So remember that domain means that it's connected in particular. All right. So let's look at complex valued functions. If we were talking about domains of functions, right? So if I have a function from any set x, I could write down I could write it in Cartesian form, right? If it's complex valued, I could have u plus iv, where u and v are real valued functions, right? So you have it's really just two real valued functions. That's a complex valued function, right? Now, if x is a subset of c, you could start taking derivatives, right? Partial derivatives. I can take the x derivative, right, of f, and that's just going to be the x derivative of the real part plus I times the x derivative of the imaginary part. And the same thing for the y derivative, right? So kind of, you do the obvious thing, right? Now, if x is a subset of the real line, well, we can just, if we say, well, let's take a derivative, it's just regular plain old calculus one variable derivative, and we're taking a derivative of the real part plus I times the derivative of the imaginary part. Basically the same idea. We can differentiate, we can also integrate. This is the way that you integrate actually in any vector space. So if I have a vector space value function, in this case C, it's integrable. And in this class, we're going to talk about Riemann integrals, really. We're not going to really have much use of Lebesgue integral, although, you might, if you know Lebesgue integral, right? I mean, it's the same thing, but everything that we do will be doable with Riemann integrals. And so if I want to integrate f from a to b, right, it's defined in some interval, then I'm going to integrate the real part plus I times the integral of the imaginary part. And I can take that basically, I mean, that's the definition. But that's how you integrate in any vector space, really. And so, one basic proposition which we sort of use all the time is that if I have a Riemann integrable function, a complex value Riemann integrable function, then the modulus is Riemann integrable. And if I take the modulus of the integral, it's less than or equal to the integral of the modulus. Basically like a triangle inequality for integrals. So it takes, maybe a little bit of trying to figure out, why is it Riemann integrable, and, why that's still true. But yeah, it is, right? So, I mean, you have it for real functions, but you also have it for complex functions. For complex functions, it might be, a little bit more not so obvious, right? But it's still true. All right. So next time, what we're going to look at is a matrix representation of complex numbers, right? Which is going to be useful later on when we look at the complex derivative.